Hello, my candidates. You're welcome to our physics lesson once again. We want to thank our national broadcaster, Uganda Broadcasting Corporation, for this service that has been rendered to us all through the COVID period of time. Let us keep at home, let us keep washing our hands, and follow the Ministry of Health guidelines so that we can be able to have this put out of our beloved country, Uganda. Once again, I am your teacher, Ojambo, Joe, and this is my contact here to take you through our physics lesson. As per our last meeting, if you remember, my beloved candidates, we discussed something to do with relative permittivity. And by the time we ended our lesson, we had left ourselves with a task of measurement of the permittivity of free space. We want to pick it up from there so that whoever could have gone through the work or whoever could have done the homework can be able to mark themselves. And it is at this point that we are going to have our lesson objectives. The first objective will be measurement of relative permittivity. Let me write the symbol. Then the second will be, we shall now be able to also look at arrangement of capacitors. And under arrangement of capacitors, we shall be able to look at basically two things. We shall look at the series connection and the parallel connection and see how to get the total capacitance when it is when the capacitors are either in series or parallel. Then finally, we shall be able to look at some examples, some worked examples. We want to keep our lesson objectives as minimum as possible so that we can be able to make them achievable. This is where I want to go today. And from what we said, we shall start with lesson objective number 1, and that is measurement of the permittivity of free space. Remember, I had left it for you as an assignment. It's now time to mark oneself. So, as we know, we have our setup, which is in this form. This is our vibrating reed switch. This is our protective resistor. Remember, whenever you're drawing a diagram, you go ahead and label protective resistor. This is our sensitive galvanometer or sensitive current meter. This is our capacitor of capacitance C. So, this is our setup and this is our voltmeter. This is our setup. One thing about this experiment, we shall say, we can begin by saying the setup is as shown in the diagram. Okay, then because of the high values we might need or because of the high voltage values we're going to have, there is need to insulate. You're going to have a very high insulation, and that is one of the precautions. So, a high level of insulation is required. So we can then go ahead and say, now that is basically the introduction. So the procedure, I can go and say, ahead and say that the capacitor of capacitance C is alternately charged, okay, is alternately done what? Charged by making contact at point A and discharged fully by making contact at point B. By making contact at points A and B respectively. That is, at point A, we are fully charging it. And at point B, we are fully discharging it. Now, after we've done that, we shall go ahead and get the voltmeter reading, V, and current reading I are noted. Okay, so you have finished the process of charging and discharging. Then after that, we shall then go ahead and get, remember the capacitor we use here is a capacitor in form of parallel plates. So what do? We shall then go ahead and get the area of overlap. The area of overlap A and distance of separation between the capacitor plates distance of separation, can I say D, between the capacitor plates are measured and noted. You realize that for every experiment I'm performing, I go ahead and record the results because I'll need them in the treatment of results. Now, what does that mean? That means we shall be able to go to the next thing. Now, at the point of discharging, if we suppose it is, that is the capacitor is completely discharged, then from what we said, the current I will be equal to FQ, where Q is the charge, F is the frequency of the vibrator, and I is the current that will have been discharged through, as we discussed earlier. Now, we know that Q is equal to CV. The PD, remember, we noted. The C, since we are talking about a parallel plate capacitor, it therefore means that our C will be equal to epsilon naught A over D. And remember, we are looking for epsilon naught. The area of overlap we have already determined. The distance d of separation between the capacitor plates we have also determined. So if I put this there, we shall therefore have I will then be equal to F epsilon naught A over D. Okay? Times our PDV. Because remember, we have put this here. Let me first of all have this one written. Allow me fix it here. Let me just extend this. From what we have discussed, we said C is equal to epsilon naught A over D. But from here, we discover that having seen that Q is CV, we shall then have I, it will be equal to FCV. Okay, so that is now where I get this from. The frequency is there. C is epsilon naught A over D, and V is the PD. Now, from the mathematics, if you went ahead and made epsilon naught the subject, because it is the one we are looking for, we shall discover that epsilon naught is therefore equal to ID over FVA. Therefore, the permittivity of free space will then be determined from this expression. Remember, the current we determined, isn't it so? The distance of separation we have. The frequency is also known. The PD is determined. Remember, we have a voltmeter and the area of overlap. Therefore, this is how we shall be able to go ahead and get our permittivity of free space. Sometimes a question can be set asking you to find the permittivity, the relative permittivity, which is the dielectric constant of the material. This one, what you would do, after you have done all this, you would again now go ahead and have this capacitor plate now filled with that dielectric and repeat the procedure. And upon repeating the procedure, you will now be able to determine the current, the PD. You can have it as the same PD because you'll have the same voltage supply, meaning that the only thing that will be changing is the current. Okay? Since then you'll be able to determine this, you will then have maybe I prime D over FVA. Now, from which you'll be able to divide these two, this and that. If you remember from what we discussed when we were looking at the dielectric constant, which was this over that. Okay? When you put all these together, you will then discover that you will now have I prime over I. That is how you'll be able to determine the relative permittivity. Take time through and try to work out this, and you'll discover that you'll be able to come up with this experimentally, meaning that you will have to get the ratio of the current, okay, when the capacitor is filled with the dielectric to the current when the space between the capacitor plates is a vacuum. So that takes us to a simple example. Suppose we look at an example, okay? And the example is as follows. If A, that is the area of overlap, is 30 square centimeters, D is 1.0 centimeters, the PD applied is 150 volts, the current I is 120 microamperes. Calculate the permittivity of air if the frequency F is set to 50 Hertz. Okay, that is our question. So my dear candidates, we are given such a question. They have said if the area of overlap is 30 square centimeters, the distance of separation is 1.0 centimeters, V, the PD is 150 volts, I is this, then we are supposed to determine this. So here, the first thing we can do is to go ahead and get our formula written. Suppose we are in position to remember the formula very well. What do we know? We know that our epsilon naught is equal to I d over FVA. We have already discovered this, isn't it so? Experimentally, more so. So we go ahead and get the other quantities substituted for. Our current is microamperes. We shall change it to amperes. The distance of separation is 1 centimeter. We shall change it to meters. The rest, I think, are okay. And even the area of overlap, okay, will be changed to square meters. So when we substitute, shall have epsilon naught is equal to 120 micro times 10 power negative 6. In other words, we are going to divide by 1 million. Then times, the distance is 1 times 10 power negative 2. Multiplying by negative 2 is the same as dividing by 100. Isn't it so? That is very right. Divide by, the frequency is 50 hertz times, the PD is 150 volts, then times the area of overlap, which is 30 square centimeters. Now, we know that 1 meter is equal to 100 centimeters. So if I went ahead and squared this, that means I'll also square the other side. Okay? Implying that when I have 1 meter squared, it will be equal to 100 centimeters times 100 centimeters, which would give us 10,000 centimeters squared. So it is on that account that I'll now divide here by 10 power 4, which is the same as multiplying by 10 power negative 4. So when we compute further, let me try to get my calculator and we work out together. I know my candidates have also reached out for their calculators. Let me stand here so that I don't obstruct you. 1 exponent negative 6, that gives us that. Then divide by 50, divide by 150, divide by 30 exponent negative 4. That has given us, is there anything we have left out? The frequency is there. And what else do we have? Okay. Well, that is what we have. What answer do you have, my candidates? I have an answer which is it 5? It is a bit low. 33 exponent negative 12. That is farad per meter. But we can cross-check and see. What was our current? Oh, let's see our current. Oh, yes. Our current is 0.21, not 120. Let us just make this correction. 0.21 microamperes. I was wondering. Remember, this is a constant, so we must be able to at least keep within the range of the value. So this is 0.21. The rest will remain the same. And I think when we work out this time, we should be able to come up with the closest answer. So I think we have corrected. Our current was 0.21, not 120. So we can compute again 0.21 exponent negative 6 times 1 exponent negative 2. That has given us, the numerator becomes 2.1 exponent negative 9. But we can further divide by 50, then divide that by 150, then divide that by 30 exponent negative 4. All right, and we have got an answer which is, I don't know if people are getting the same answer as mine. This time I have 9.33 exponent negative 11 farads per meter. And that is the value of the permittivity of free space, which we have done what? Which we have obtained. So, objective number 1 has been achieved. Determination of the permittivity of free space. Then from there, we can proceed and look at arrangement of capacitors. We have discussed the capacitors right from the beginning. First of all, we talked about what they are, and we have looked at all these. So we want to see, how can they be arranged in a circuit? They can be arranged in series, and they can be arranged in parallel. Now, when they are arranged in series, what do we mean? When they are arranged in parallel, still, what do we mean? And that's what we want to discover, okay, at this moment in time. Let me erase this. So, this is what we want to look at, okay? Arrangement of capacitors. How can we have them placed in a circuit? So, capacitors can be arranged, arrangement of capacitors. The capacitors can be arranged in different ways. We can have them arranged in series, we can have them arranged in parallel, or they can even be arranged as a combination of both series and parallel. Let us start with parallel arrangement or parallel connection. So for the parallel connection, we are going to discover that we shall have the capacitors arranged such that the corresponding ends are joined together. Suppose the charge on this one is Q1. The charge on this one is Q2. Charge on this one is Q3. We imagine we have 3 capacitors which are arranged in parallel. So this is going to be negative Q. Since they are closed by induction, this is negative Q. This is also negative Q. This is Q1, negative Q1, negative Q2, negative Q3. And you have connected them to the same PD supply. V. Now, because they are in parallel, you can see all these are interconnected and they go to this positive. It means that the PD across these 3 capacitors are the same, or the PD across these 3 capacitors is the same. What does that imply? That means that each of them is going to have a different charge. Why? They have different capacitances. They have different capacitances. So in getting the total charge, what are we going to do? The total charge is therefore going to be given by the sum of the charges on each of the capacitor plates. So that means we are going to start from that point and say that total charge, so we can say consider, I can write on the side, consider 3 capacitors of capacitances C1, C2, and C3 arranged in parallel. Okay? We have discovered, or we have said that the PD across each is the same. The PD, that is the potential difference or the potential drop, across each capacitor is the same. Okay? Total charge Q is equal to, we've seen that total charge Q will be equal to the sum of the charges on each of the capacitors. So it is Q1 plus Q2 plus Q3. Okay? But we know from the relationship we discovered between charge, PD, and capacitance, we shall therefore discover that Q1 will be equal to C1V. Remember, the PD is the same, isn't it so? Then Q2 is equal to C2V, and also Q3 is equal to C3V. So what do we do, therefore? We can now go ahead and substitute each of these into the equation we already have. So I can therefore say Q will be equal to C1V plus C2V plus C3V. But since V is the total PD and it is a common value, I can therefore go ahead and do what? Have it factorized out. At factorization, we shall have Q is equal to V into C1 plus C2 plus C3. So if I went ahead and divided here by V, we shall have Q over V is equal to C1 plus C2 plus C3. Okay? But now remember, this Q is the total charge. This V is the total PD, which therefore implies that Q over V, I beg your pardon, this is a V, not a C, is equal to C, where C is the effective capacitance. Therefore, our total capacitance will be equal to C1 plus C2 plus C3. So this is the expression for our capacitors which are in parallel. So what do we discover? This shows us that when you have capacitors, even if there were 10 or 5, and you place them in parallel, that is, you place them across each other, it would therefore mean that the total capacitance is going to be given by the sum of each of the capacitances. And what does that mean? This means that the capacitance in this case is going to be very big. It will have been increased. Why? You see, if you simply add, you imagine, let's look at something very quick here. You imagine you have capacitors of 2 microfarads, 3 microfarads, and 1 microfarad, and they are in parallel. And I went ahead and found the total capacitance. It would simply be, C would be equal to 2 plus 3 plus 1, which is equal to 6 microfarads. So you can see that the value 6 is bigger than even the biggest individual capacitance, which is what? 3. So by placing capacitors in parallel, you will be increasing the capacitance. So that is the relationship. Let us look at the second relationship, and that is series. Now, for series connection, my dear candidates, we shall connect them end to end consecutively. Okay? We've seen trains, and you'll see the train wagons. When you see the train wagons, each wagon is connected to the other consecutively, and that is what we mean by the series connection. So the second one is we call it the other one. We shall call this to series connection. For series connection, we shall get our PD source and connect it across these. Imagine we have, let me have 3 of them, and they are connected like this. I think you can see what we're saying. They are connected end to end. This is the positive terminal of the battery. This is the negative terminal. And the PD there is V. Now imagine this is plate A and this is plate B. So charge will be transferred from plate A to plate B by transfer of electrons from plate B to plate A. Okay? And meaning, if this is negative Q and this is positive Q, now these plates, remember, are close. If you remember what we said, that they are normally close to each other, the pair plates. By reducing the distance of separation, you'll be doing what? Increasing the capacitance. So you find that by induction, since this is positively charged, this one will be induced by unequal but opposite charge. The charges are equal in magnitude, but the signs will be different, because we know by electrostatic induction, once you have a positively charged board and you bring one which is neutral close, it will induce a negative charge or a different charge. Then this will have positive Q, this will have negative Q, and then eventually this will be positive Q. Now, it is this setup, or it is this genesis, that enables the charge to be the same. Okay? So we are consider 3 capacitors of capacitances C1, C2, and C3 in series. Okay? Now we have discovered that the charge on them is the same. However, the capacitances are different from what we have just stated. Now, because the capacitances are different, what does that imply? The voltages will also be different. So PD across this can be V1. PD across this can be V2. And PD across this can be V3. Okay? So what does that imply? This tells us that the total PD across the capacitor plates will then be got by the sum of the PDs, or of the potential differences across each of them. So what do we discover? Charge on each capacitor, that is the charge stored on each capacitor, is the same. Okay? So total PD V will be equal to, we've said it is the sum of each of the PDs across. So it will be V1 plus V2 plus V3. But we can go ahead and get the PD across each of them. But V1 will be equal to, remember, charge is the same, isn't it so? So Q over C1. V2 will be equal to Q over C2. And finally, V3 will be equal to Q over C3. So we go ahead and substitute this into our expression. And what does it become when we substitute? We shall then have from V equal to V1 plus V2 plus V3, we shall substitute for each of the potential differences. We shall then have Q over C1 plus Q over C2 plus Q over C3. We now discover that our charge is constant. So what do? We can factorize it out. Isn't it so, my candidates? So upon factorizing, we shall have V is equal to Q into 1 over C1 plus 1 over C2 plus 1 over C3. When you divide through here, this is divided by Q, divided here by Q, this Q will cancel with this. So we shall then have something which is going to be in the form of, I can use the space here. Let me also erase this. I know we have noted this down. From here, we have now seen we have V over Q is equal to 1 over C1 plus 1 over C2 plus 1 over C3. What does that culminate into? We know from Q over V equal to C, it implies that if I find the reciprocal, I'll then also find the reciprocal there. Isn't it so, class? That means from Q over V equal to C, it will imply that V over Q will be equal to the reciprocal of the capacitance. Now, from what we have already discovered, C is going to be our effective capacitance. Why? The PD, V, is the total PD from what we have seen here. And the Q is the total charge. Therefore, that means that therefore, we can deduce and say 1 over C is equal to 1 over C1 plus 1 over C2 plus 1 over C3. Implying that the total capacitance of any three capacitors which are connected in series with each other is given by this relationship. Okay? Now, before we continue, I want us to relate with what we looked at earlier by looking at this example, a quick one. Remember, we looked at initially the three capacitors of capacitances, 2 microfarads, 3 microfarads, and 1 microfarad. When they were in parallel, we got a total capacitance of 6 microfarads. Let us check and see. Suppose we have these ones now connected in series. If you have them in series, we have discovered that total capacitance will be given by this. So it will be 1 over 2 plus 1 over 3 plus 1 over 1. The LCM of all these will be 6 is equal to 1 over C. 6 divided by 2 is 3. 3 times 1 is 3 plus 6 divided by 3 is 2. 2 times 1 is 2 plus 6 divided by 1 is 6. Isn't it so? Am I right, class? Yes. Then times 1 is 6. Isn't it so? So from there, what do we discover? You'll have 1 over C will then be equal to, the numerator is going to give us 5 plus 6 is 11 over 6. So therefore, our capacitance will be the reciprocal, 6 over 11. 6 over 11 microfarads. Remember, this is physics. We can change this to decimal. Allow me to do that very quickly. That is giving us, in decimal, it is going to be 0.5454, yeah, something like that. Yeah, it is 0.54. So our total capacitance is 0.545. Allow me to write it to 3 significant figures, 545. Now, microfarads. What do we discover? We discover that the capacitance here is less than the capacitance we had earlier. And more so, when you compare it with the individual capacitances, you discover that the total capacitance is even less than the smallest individual capacitance. So therefore, this tells us that by placing the capacitors in series, we are greatly reducing the capacitance. Okay, so these two have given us what we are looking at. A case can be given to you where you have only two capacitors in series. Suppose you have only two capacitors in series, something like this. What does the total capacitance become? This is V, this is Q, this is negative Q, this is positive Q, this is negative Q. I have taken this speed D to be V2, then this speed D here to be V1. Of course, you'll start from here. But I want us to start from where we had the three capacitors. Suppose we have worked out and gone up to this point, 1 over C1 plus 1 over C2. At this point, since I have just two of them, I can proceed and get the LCM on the right-hand side, okay? So we shall have 1 over C is equal to the LCM of these two. I can have it as C1, C2. So C1, C2 divided by C1, my candidates, what do we get? C2. Then times C2 is going to be C2 plus. C2, C1 divided by C2, we shall remain with C1. Isn't it so? Times 1 is going to be C1. Now, when you play around with these unknowns or letters, we shall discover that C into C1 plus C2 will then be equal to C1, C2. Our target is to make C the subject, isn't it so? So therefore we shall have C is equal to C1, C2 over C1 plus C2. Now this one is very, very important and essential. We shall discover how useful it is. You shall discover how useful it is in our discussions. How? When you have two capacitors connected in series, we have discovered that two capacitors will then be given by the product of the individual capacitances, okay, divided by their sum. So you don't need to go all this way here. You don't need to go this way. You can simply be able to memorize this, okay? So this is a very important expression. However, we should bear in mind that they can always ask us to derive it, my dear candidates. And this therefore takes us to worked examples. Worked examples. Worked examples. We want to look at a few examples. And from my examples, we shall be able to look at so many other aspects. And since our lesson is almost coming to the end, we are going to be able to have our examples discussed greatly or more when we meet in our next lesson. But of course, bear in mind that we have been able to achieve some of our lesson objectives. One of them was measurement of epsilon naught. And remember, it was given to us as an exercise. So we were marking ourselves to see whether we had been able to do the work correctly. We also looked at an example there, from which we looked at the arrangement of the capacitors. We've seen the parallel connection, and we were able to get the effective capacitance, and looked at a very simple example. Then also looked at when they are in series, and also went ahead and looked at an example, which has finally taken us to a point where we would look at more of the other examples. Now, let us write this question so that when we come back, we are able, in our next lesson, we are in position to have the questions attempted. Okay, now, because I'm not going to dictate, I need to write it down. I believe we can start from here in our next lesson. Stay home, keep sanitizing as much as you can, wash your hands, even much as you know that there is no food to eat. It is one good way of ensuring you are keeping that virus away. Till then, I remain your teacher, Ojambo Joe. In case of any questions, you can always reach me on that number. It is also the same number I use on WhatsApp. When you send me questions which have solutions attempted so that I can be able to correct you. Don't send only questions, my dear candidates. We should now be in position to attempt as many questions as we can. Thank you very much. Have a blessed day.